Hey out there, everybody. I just want to talk a little bit about this force the line experiment that apparently there's some money being raised for this. I wanted to talk about that really quick. I wasn't aware that money was suddenly being raised for that. I mean, I remember when Brian Mullins suggested this many years ago, but apparently it has come back up, and Mr. Sensible here has made it somewhat famous. I found out about it by watching Mr. Sensible. So I want to spread the word a little bit that's out there. And I think, I like to think that there are some few flat earth believers who occasionally watch my channel, and maybe you don't watch Mr. Sensible. And so hopefully I can help you out a little bit by telling you, don't put any money into this, okay? I'm not going to say it's a scam. Is it a scam? No, I don't. I mean, I don't think it's a scam. I think the person who's trying to do it is genuine in his belief and really hopes that if he raises the money, he can put that money towards this goal. I'm here to reach out to you as a friend to the flat earth community. I'm not a flat earther, but I want to be there to help you. The problem here is, what would the point be of doing this experiment? It will not convince any glober to change their mind. If you're thinking, finally, this is the experiment that they cannot deny, I'm going to tell you right now, pump the brakes. They've already denied it. I, as a glober, I will do a quick analysis here in a minute and show you, no, I do not believe that you can do this experiment with enough precision that I will accept the results. No, I will not. So don't bother doing the experiment. Look, if you're trying to convince somebody, the flat earthers, they already believe. You don't need to convince them. The globe earthers have already rejected this experiment. It's not going to convince them, right? So if you want to do an experiment that will convince a glober, I can give you a list of those. I've made a list of 20 of those in an old video of mine. I can give you a list of those. I can give you a longer list. I can make up more. There's lots of things you could do that would convince me at least to look into it deeper, right? Long list of those. This is not one of those, and let me tell you why. Let's see here. Okay, it's not going to work is why, and here's why it's not going to work. The suggestion is something like, we're going to take two parallel rails, like a fence. I'm going to start them off here. I'm going to make it a mile long. I'm going to make a fence that's a mile long. The top rail will use a plumb or a level to make it level with the gravitational force. I don't know, level. It'll be level, right? The bottom one, we will make it square. So the idea here is that if the Earth is curved, then the level one at the top will curve along with the curvature of the Earth. And the straight one on the bottom will not curve, because we're not going to be leveling that. We'll be shooting it straight. If the Earth is curved, then using a level, the globers say the top beam is going to curve downward, but this bottom rail will not use a level. It will just be perfectly straight, and therefore it won't curve downward. He suggested, I believe he suggested doing a mile, like we do a mile long. And he said, well, he didn't say, but we all know, right? In a mile, the globe is supposed to have an 8-inch drop, give or take. So I've exaggerated it, obviously, here, but let's say over our mile, we're looking for the one rail to drop down, the other one to go straight. So the gap that you start with should drop down by 8 inches, as near as I can tell, right? Okay. So if we make our fence out of 10-foot long sections, That means there are 528 sections of rail. And we're looking for an 8-inch drop over that distance, right? And so what we're going to do is we're going to build the rails. We're going to go to the end. We're going to go down to the end until we've built that last rail. We're going to measure the gap in between. We're going to measure the gap here and measure the gap here. And we're looking for an 8-inch difference. To have any confidence in this result, the end, we're looking for 8 inches of difference. What if we don't get 8 inches? What if we get 4 inches instead of 8 inches? What would that mean? That would mean that either the Earth was flat and the rails deviated by 4 inches, or the Earth was curved and the rails deviated by 4 inches. The 4-inch result is the breakpoint between flat and round. It's the point which you cannot tell the difference between flat and round, right? So if you measure 4 inches instead of 8 inches, it means absolutely nothing. So that must be avoided. 4 inches doesn't sound too bad until we consider that we're doing this over a mile in 528 sections. So let's take a look at that. And actually, it gets a little bit worse. We're trying to come in at 8 inches different. So if you think about what does 4 inches different mean, that means you can't tell. You don't know whether you got your 8 inches. Was there 8 inches and there were 4 inches of error? Or were there 0 inches and there were 4 inches of error? Either way, it's 4 inches of error. No good. So we have to have less than 4 inches of error. And that means, since there's 2 rails, each rail must have less than 2 inches of error. If the rails cannot be guaranteed to be within a margin better than 2 inches of error, then this whole experiment means nothing. That's the problem. If they curve towards each other by 2 inches, now they appear to be 4 inches closer together than they should be, right? Or if they veer apart by 2 inches, now they're 4 inches too far apart. Okay, so that's why we must have the entire rail correct within less than 2 inches per rail. If it's like 1.9 inches, that's really not good enough, really either. You want it much less than that, but the hard limit is 2 inches. So what does that mean? There are 528 sections. So if you just take 2 inches and you divide that by the 528 sections, that means each section must be precise to within 0.0038 of an inch. So better than 4/1000ths of an inch at each joint, right? Imagine trying to join up these 2 beams, and that joint there cannot be off by more than 4/1000ths of an inch. 4/1000ths of an inch. What is that in? Okay, I went and looked it up. That's less than 1/10 of a millimeter, right? So we're going to make this joint, and the joint can't be off. It can't be too high, can't be too low. It has to be exactly the same height within less than 1/10 of a millimeter each time, 528 times, top and bottom. And right? And the beams have to be true, right? If the beam is warped or crooked in the slightest, it must be less than that much deviation. So as an angle, those 10-foot beams are true to within 0.0018 degrees. So 2/1000ths of a degree is how straight those beams are. They must not bend, they must not flex, they must not have bumps or ripples within 1/10 of a millimeter, right? This has to be perfectly smooth, perfectly straight to within 1/10 of a millimeter over a 10-foot section. Now, I don't know where you think you're going to get that or how you would assemble that, but unless you can somehow show that this is the case, that these are that straight, nobody is going to believe you. No glober will believe that you somehow lined up 528 joints, each so straight and so true, and that none of those joints, the angle was off at all, and that those beams were that smooth, and that these metal beams, presumably using metal, as wood certainly is not that accurate. Maybe you use steel. The steel is flexible, right? Steel is known for being particularly flexible. It's going to flex under its own weight by more than 1/10 of a millimeter. How are you preventing that? How is it, right? This cannot work. Don't put money into this. Save your money. There's other videos that talk about how precise the right angles need to be at the joint, and it's ridiculous. It's, you know, it's an unachievable number. I haven't seen them point out, but the top rail is even worse. The top rail, the curved rail, is harder because we're deliberately bending that one, at least according to the globe model, right? If you believe it's flat, then we have to keep it straight, and that might be easier. But if it really is curved a little bit, then how are we going to join those up and make sure that we're straight on the right curve? We can level it to the right angle, but how do we get each beam to the right height? I don't see any way to do that, because remember that height precision we're asking for is 1/10 of a millimeter. So how are you planning to do that? It doesn't make any sense at all. I'm sorry, it cannot work. If you want an experiment that can tell the difference, let's work together and come up with one that you like. If you want a straight line, you know, you've seen a million laser tests. They're always trying to shoot lasers over water, and you've heard the rebuttals. You can't do that because of refraction. But there are things we will agree to. Do it from mountaintop to mountaintop. Just sight from one mountaintop to another mountaintop over a valley, and just use straight line of sight. You don't even need a laser or anything. Just look and use leveling, right? Just like you want to do, just like this one. We were going to use leveling to keep those bars, to see if the bar curves or if it goes straight. Do the exact same thing. Use an auto level, use theodolite. Much, much cheaper than trying to build a mile-long fence to these kinds of tolerances.